I'm Matt Carrick, and Ari O is going to be talking about some of the work she's been doing later, but I'll get us started on TorchSig. So TorchSig is simply kind of the core idea is it is a system for RF machine learning. There's two main branches if you really break it down. There's the machine learning side, there's what the models are, there's how do you train them, those interactions, and then there's also the signal generation. So we'll talk about that more a little bit, but it's all the different data sets we can generate, the different formats, and then so TorchSig puts all those pieces together to make a machine learning system. So if you go to torchsig.com, you can download the source code, you can download papers, we have pre-trained models. Some of that will be changing in the future, but it gets you a good start. And then that will link you to the GitHub. So if you're interested in running it, you can go today, right now, do a git clone, download all the source code. We've got a bunch of new examples and things there for you to run. So I said, we've got some machine learning models. We've got narrowband and wideband. So narrowband, you can think about this as if it's been channelized already. So it's at complex baseband, it's resampled, and it's as if it's been time-aligned. So it's been put through an energy detector, and then we've got a wideband model, which is it operates on spectrograms. So you can look at signals in time and frequency. So my favorite part, the data set generation. So we've got a couple different waveforms that we can look at. We've got FSK, GFSK, all the QAMs, all the PSKs. So we go through, generate those for you, and then you can apply the machine learning to that. So we've got spectrograms, and you see a bunch of different waveforms on here. So at the top, we've got 8 FSK, 128 QAM, these kinds of things. So it generates a single signal for you. And then at the bottom, it will generate a bunch of overlapping signals, higher complexity for the machine learning to train against. All right, recent updates. So we have a couple updates on the website that you can download. It's making things faster, less memory, reducing size on disk, and we also added a bunch of DSP updates, new examples, those kinds of things that are a much better tutorial for using TorchSig for new users. And now Ari O will talk about the rest of her contribution for synthetic spectrum generation.
Hello, so I will be talking about two novel things that are new about TorchSig. First is the synthetic spectrograms, and second is a new GNU Radio block. So just starting out with spectrograms. Spectrograms are just a visual way of representing signals across a spectrum. And this is very important because now your signals are in the image domain, and you can use a lot of image-based machine learning techniques to train a model to detect these rather than in the IQ domain. You can imagine these models drawing a bounding box around these signals at the correct frequency and time. So I feel like everyone knows that. But getting more about synthetic spectrograms, currently TorchSig has the ability from IQ data, like SIG53 and wideband, to convert to spectrograms, but that's very computationally expensive. Creating just synthetic spectrograms straight up in the image domain is a lot faster, and it's a lot more quicker, and this results in being able to quickly create a data set for your machine learning models. And I'll talk about two main things about these synthetic spectrograms. One is augmentation. So if you have a signal, you can augment it. And two is just general creation of signals, which I'll go into in a little bit. But this solves a lot of the problems in terms of the data set problems you might have with IQ data. The first is basically being able to augment signals. So let's say you have a signal of interest and you want to train a model like pretty quickly. To detect this, you can use few-shot learning, which is basically training a model on only a few examples to detect this particular signal. And you can do this by basically taking those few examples that you have of your signal of interest, train a model, and use our TorchSig tools to augment this signal. So it's not just cleanly throughout the spectrogram. It has noise, it has frequency hopping. You can see a little example there of recycling narrowband. And this is really valuable in case you want to quickly train a model to detect a particular specific signal and like augment your current signals that you already have. But going into like creating your own signals, like our typical modulation schemes, we can also do that from scratch, just simply in the image domain. So here's an example of creating like a chirp-based waveform, and that's like a lower-like waveform, and you can see this is all done in image domain. There's no IQ data behind this, but I'd say it looks pretty realistic. And going into like how that all works, we use context-free grammar, which is a mathematical concept of creating very complex patterns. And you can see more examples are in the code, but you can really up your complexity of these custom signals you can just create yourself without having to go out and collect it yourself. And you can see here, this is how you can just put it all together, these composite spectrograms with your own custom signals. And just to remind you, there is no IQ data involved in all this. This is all just pixels and images. So feel free to throw your image-based machine learning models at this and have it learn. And we've proved that training on synthetic spectrograms translates very well to the real world. Taking a little fork in the road to the GNU Radio, which is the conference we're at, we have now created a GNU Radio block for inserting your own machine learning model into your flow graph. So in this example, we've trained YOLO V8 on the ISM band. We've trained it on, to be clear, not synthetic spectrograms. That was just the previous feature. This is just on our dataset wideband 653 on those images. And we've trained it to detect signals, and this is an example of the flow graph, and this is an example of some of the parameters you can do in that GNU Radio block. It's not fully featured, but obviously still in development, but you can parameterize a bunch of aspects of this model. And here's a quick screenshot, and we're gonna do a quick demo in like a couple of minutes to show like this in live time, but I'd say it does a pretty good job of quickly picking up signals and running that model in real time. And just to go over some future work, obviously we are always trying to improve our data sets, and especially allowing users to use TorchSig with their own custom data sets, especially integrating with Label Studio. And as always, like trying to add more integrations with machine learning models like Hugging Face and PyTorch, and improving our synthetic spectrograms. There's a lot of work that could be done in that space for creating even more realistic or complex synthetic spectrogram signals, and not all of the modulations we have currently implemented. And lastly, we have more modulations coming in the way, so the name SIG53 will have to be refactored because there's more than 53 signals, but these are exciting stuff that's coming up for TorchSig. We'll run the demo real quick. I'll just take this HDMI, but if you have any questions, you can think about it. So this is the flow graph that it's pretty much the same as given in the screenshot, YOLO trained on our wideband data set. And this is just it detecting signals in live time. I know it's a little fast, but this is just live right now on this laptop. So I can take questions while this runs.
All right, thank you very much. Where are the questions? We got one here, got three of them, so.
Hello, I have a quick question. So when you talk about synthetic spectrograms, so there's no phase information anymore, like you're only using the magnitude?
Yeah, so as you know, like a lot of information is lost when you translate to spectrograms. So there's no phase information, and it's very hard to recover phase information from spectrograms. So yeah, no phase information.
And how did it compare with the full IQ based spectrograms? Did you guys do a comparison?
Yeah, we did a comparison, and it's just, they both work really well. You can just choose which data set, whether the IQ data set or the spectrogram data set, but the images just have this edge over, like, it's much faster, it's much quicker. If you need something quick and dirty, like, get it done. But obviously, if you want the full, like, specific in-depth, like, phase, with, like, phase included in your model, you should probably use the IQ data. So, hope that answers your question.
So I'm wondering about like unknown classes of modulation. Like, is your energy detection algorithm able to pick out an unknown class of modulation that you have not trained your model on?
Yeah, so going along that, I think we want to be able to. Is your question like how does it do on modulations we haven't seen before? Is that your question? Okay, gotcha. Essentially, by adding these augmentations and these synthetic spectrograms, we're hoping that you can train models that are more robustly or adaptable to these like unknown signals, and that you can't just like generate. That's quicker to generate than IQ data, but obviously you can pick these signals up yourself. But that is like the general idea, is that being able to create these synthetic spectrograms, you can quickly have a more generalizable model, or you can make your model very specific and fine tune it. So that was the idea.
Hi, I'm with them. But just to clarify, does generalize sometimes. We're working on different ways of helping to improve generalization of the models to it'll pick up unknowns. It doesn't always do a very good job. It's very important to fine tune on the specific type of models and the specific spectrum. It'll perform very differently. This is trained specifically on the ISM band. If you try to run an HF spectrum through here, it's gonna crap, right? So you gotta fine tune on that particular spectrum band. Also, the data sets are very dynamic. You can, it comes out as complex IQ, and we have a bunch of transforms. So you can generate spectrograms based off the IQ. You can break it up in its real imaginary components. You can do whatever you want to the data at that point. You can write your own transforms and put them in there to do whatever you want with the data. But there's two different types of spectrograms. There's the spectrograms based off the IQ, and then there's the purely synthetic image domain spectrogram. So just to clarify.
What's the minimum hardware that you need to run TorchSig?
I would say a monitor. It depends on how long you want it to take to train, how long to take generate data. A modern laptop. So we're running just a, I don't know, reasonable laptop with a B210. If you wanted, I would suggest a GPU with it. That's probably the minimum, but it's nothing beyond that.